Alright, welcome back, ladies and gentlemen. In this video we are going to be looking at some examples using conservation of mechanical energy. So I've got three examples specifically in mind here. In the first one, let's look at a baseball game, and we have the ball hit by the bat, and the ball takes a trajectory, and let's say we have a home run hit, so the ball is caught by a fan who is sitting in the stadium somewhere, and so the elevation of the ball when it is caught is different than the elevation of the ball when it is hit by the bat. There's also some initial velocity here, and there is some final velocity here. Okay, and we have this difference in vertical position from the initial to the final situation. Just call it a y. You might think of that as a change in y value. Sometimes you'll see this called an h for height. That's fine. So let's give some values here. Let's say we want to find out how fast the ball is going when the fan in the stadium catches it. Well, we will need to know the initial velocity. Let's go 36 meters per second. We will need to know the mass of the ball. Baseball is around 0.15 kilograms. And the difference in height. The seat for this fan is located, let's call this 7.2 meters above where it is hit from the bat. Now it sounds like an odd number, but the bat might be some sort of arbitrary or random distance above the ground, depending on who's holding it, how they're swinging, so on. Not too important. We have that distance. So we're looking for this final velocity. Okay. So there is our situation so far. Now, an important question. We're going to solve this in terms of energy, mechanical energy. So what do we know about mechanical energy? We have to make an assumption about friction or drag forces, about non-conservative forces, assuming there are none. No drag, no friction. Then what do we know about mechanical energy? Well, the initial amount is going to equal the final amount. Energy will be conserved. All right. And from this, we can start breaking this down. So, mechanical energy. I'm going to give you a few seconds. Try to recall what mechanical energy consists of. Kinetic energy. And so, we're going to add kinetic energy to the potential energy, those two initial values. And over here, same deal, but we're talking about the final values. Now there's something interesting here. If we're going to look at the position, the vertical position of the final catch of that final velocity where it occurs, as being 7.2 meters high, then this initial position will be 0. So you might think of y initial equals 0. If y initial is 0, then there's no stored energy based on the position of the ball right here. So if there's no stored initial energy, this goes to 0 because 0 height above the reference level. This is our reference level. That's our 0 mark. So this simplifies, and we're looking for a final velocity. And in order to do that, we have to first really solve for the final kinetic energy of this ball. Solving for final kinetic energy is going to leave us with initial kinetic energy minus the amount of stored energy, the amount of potential energy in the final location. Okay, we can start to break these down a little bit for ourselves. Let's look at the value of this final kinetic energy. We're going to say, well, initial kinetic is going to be 1/2 mv initial squared. Please keep track of your exponents. We're going to take away the stored energy, potential energy. This is due to gravity, so when it's due to gravity, we say mgh. Or remember, it could be h. Here we're calling it y. It really doesn't matter what you call it. You're thinking of that vertical change. So there we go, and we can see something though. I mean, in one or two instances in the past, we've looked at the situation where mass cancels out, right? Well, certainly if we wanted to, we could factor mass out of these two terms, but it won't cancel because we are stuck with kinetic energy here initially. We'll see later on that it sort of becomes unimportant what the mass is. Now, we can plug some numbers in. The mass was 0.15. The initial velocity was 36 meters per second squared. Again, mass 5. G is 9.1. And the value for y, remember that was the 7.2 meters. Okay, running out of space, we can go to the next page. Try not to squeeze it in too small for you. So we're on page 2 now. And we're getting a value for this final kinetic energy of, well, if I look at the two terms, I get 97 joules of energy, take away 11 joules of energy, accounting for some rounding. So the final kinetic energy ends up being 86 joules. Awesome. That might have been a question we would be asked, to find the kinetic energy when it is caught by the fan. But beyond that, we are specifically asked for the velocity. So there's our strategy. We're going to use the final kinetic energy to find that final velocity. And we know the kinetic energy is, in a basic sense, just 1/2 mv squared. And this happens to be final velocity since that's our final kinetic energy. And we know the value there. We're going to solve for final velocity. And the equation looks like this. 2 times the final kinetic energy divided by the mass. I'll plug some numbers in there. 2 times 86, and the mass is 0.15. And so our final velocity becomes 33.9. And really, that's because of sig figs, that's just going to round to 34 meters per second. Awesome. So what we see, think about this. Think about what's going on. We saw an initial amount of total energy. Again, I'm showing you my notes, not the one I drew for you. Initial total amount of energy is all due to kinetic. In the final position, the total energy is due to some kinetic and some potential, some amount of stored energy based on this height above that reference line. And the greater the height, the greater amount of energy stored, well, the less kinetic energy there's going to be. Thanks for watching. I'll show you some more examples in just a minute.